Hey guys, welcome back to chapter 13. This is going to be our last video in this first half of chapter 13. So if you're in my online course, this is the last video in 13a. So the second half of this chapter has a lot of math. So far we have looked at equilibrium constant K. We calculated it based on numbers at equilibrium. But that's not really how it is in reality. Things are a little bit more complicated when it comes to chemical equilibrium. So that's what the rest of this chapter is going to acknowledge is, well, how are these things done in quote-unquote real life? So to kind of organize our thoughts through the rest of this chapter, whether it be for the A going into B, here's kind of our thoughts. There's different types of math problems that we can do. The first type of math problem is to determine the equilibrium constant. So there's our problem that says, at equilibrium, the concentrations are. We can just plug that into the equation and solve. And we did that back on slide 25. We did similar calculations with the reaction quotients. We've done a few of those already. In this video, we're going to talk about this one. So determine the equilibrium concentration of one unknown. So we know the constant, we know most of the concentrations, we're just going to do some simple algebra to determine one unknown. Then the second half of the chapter, so for my online students, 13b, will entail the following, so kind of a line in the sand, right? The second half will entail determining equilibrium concentrations and Kc, when we know a lot of information, and then ultimately determining equilibrium concentration in Kc when we don't know a lot of information. The reason there's a line in the sand there is the last two bullet points require a new tool, a new tactic to solve. So we'll introduce that in a later video. But this video, let's get started on that one. We're going to determine equilibrium concentration of one unknown if we know Kc. So let's just dive into an example and see what this looks like. So here's our equation. COF2 will react with carbon dioxide and CF4. And we know the equilibrium constant for this equation, and it's 2. That's a very common thing. So these equilibrium constants are in fact constant. It's likely that we could know or look up that information for a given reaction. So that's really a little bit more realistic. We know that value. We did an experiment, and then at equilibrium, we determined the concentration of the reactant was 0.255, and we determined the concentration of CF4 was 0.118. We want to know what is the equilibrium concentration of carbon dioxide. Now I could see this in a real world. Maybe I can reach in and determine concentration of reactant. I can reach in, determine concentration of CF4. Carbon dioxide, though, that's a gas that just kind of evaporates off. Maybe I can't measure that. Maybe I can math it out, though. So the first thing we're going to do for this problem is we are going to write the equation for the equilibrium constant K. So that's going to be how we start a lot of our problems. So equilibrium constant for this reaction is concentration of products over concentration of reactants. Carbon dioxide, CF, sloppy right now, sorry, 4, and then concentration of our reactant. I did not give you the states for this one. If I don't give them to you, you can assume that everything will be included in the equation. So now I'm going to plug in what I know and solve for what I don't know. So I know the value for K. It gave me the equilibrium constant is 2. Coming over here, reactants over products. It doesn't give me the value for carbon dioxide. That's actually what we are solving for. It does give me the equilibrium concentration of CF4, and that's 0.118. And it gives me the concentration of our reactant, which is 0.255. So to solve this, we're going to do some simple algebraic rearrangement. So to get this fraction to go away, I'm going to multiply by 2.55 to get that out of the denominator. So that cancels. Whatever I do to the right side, I also have to do to the left side. So multiply by 0.255. So cleaning this up, we've got the following. We've got 0.255 times 2 equals carbon dioxide times 0.118. At this point, I'm just going to clean up this 0.255 times 2. So 0.255 times 2. And I'm just going to erase it just for the sake of space. So multiplying those two numbers together gives me 0.51. Now I want to get carbon dioxide, so I'm going to divide by 0.118. So those cancel, but whatever I do to the right side, I also have to do to the left side. So from this step, I get the concentration of carbon dioxide is, I'm going to plug this into my calculator, 0.51 divided by 0.118, and I get a value of 4.32. And then we also always want to consider units. So we know this is a measurement of concentration. So the units here are going to be, oh gracious, are going to be molarity. So really straightforward, easy example. If we know Kc and we know everything but one of the concentrations, we can calculate for that one unknown with some simple algebraic rearrangement. And so there's just kind of a cleaned up version of the math that I did. That's the end of the first half of this chapter. That's the end of my online students this module. More videos to come in the second module. I hope you guys found this helpful.